Hello, following the video on Vitali coverings, I could talk about Besicovic's theorem, but I decided to do a more fun one where we add weights and prices to the balls in the collection of Vitali covering and still deduce some interesting results. First, I have to introduce some notation. So the characteristic function of a set A is a function on the space. So X is a metric space and A is a subset of it throughout, which is non-empty. So this will be 1 if X belongs to A and 0 if X does not belong to A. With this notation, we can easily rewrite the relation that a union of balls covers a set A in terms of these characteristic functions. So you can check that this will happen if and only if this function, characteristic function of A, is less than or equal to the summation of the characteristic functions of these balls over the same index set. Of course, the right-hand side could be infinity if too many balls cover the same value X. The reason I introduced this notation is apparent because that appears right in the statement of the theorem of interest. You are in a metric space, you have a non-empty set A, and there is a collection, a countable collection of closed balls that cover the set A, but the caveat being that it's only a weighted covering. Every ball comes with a weight, and the ball BI, so you can think of these BIs, it will be helpful if you think of them as numbers less than 1 and bigger than 0. That's an interesting case in all of the stuff that will follow. So you can think of them as fraction. So every BI, even if X belongs to BI, it only covers a fraction of it. So if this X is in B1, X is not necessarily covered. So X is a point in A. Suppose this is a point in the set A. So we need to prove, we need to be able to cover, we need to have summation of AI characteristic of BI bigger than that. But this will be summation of those AIs where BI actually contains the point X, because otherwise the characteristic function is 0. So if B1 is one ball which contains X, it contributes A1. But then if A1 is less than 1, you are not yet covered. So you need some other balls. Maybe this is ball number 5. Therefore, that covers a 5% of the contribution, and maybe now they add up to bigger than 1. But it could also be that for some X's, you need infinitely many. For example, let's say AIs are kind of a convergent sum, 2 to the power I. Then you need the help of an infinite number of balls to just beat the value of 1. Okay, so that's how you should think about the weighted covers. But then also there comes prices for the balls. So similar to Vitali covering lemma, we will pick a special subcollection of balls from the original collection. But this time when you choose a ball, you have to pay a price, a non-negative real number. The claim of this theorem is that you can choose a subcollection so that the price you pay is no more than this number here. So you choose only a special amount and types of balls, you'd rather pick the balls with smaller price tags. However, you also need to satisfy this other condition that the union of 3 times dilated balls covers A in the original classical sense of just union of sets. So on the one hand, you want to pick many balls so that you can cover A. But on the other hand, every time you pick a ball, you pay a price. Prices here are the only obstacle because we don't require disjointness. But that's very important for this theorem. And also the interpretation of this inequality I have is that this is kind of the weighted average price. If you think about AIs as being fractions, so this is really a weighted average. And what the theorem says is that you can do this covering no more expensive than 8 times that. So why did we prove this theorem in 2021? Because we applied it, we were actually originally interested in the case where these prices were actually given in terms of the diameter of the balls. And these, of course, you can guess, have something to do with Hausdorff measures. And we needed the stuff so that we could prove the Eilenberg's inequality, also called the coarea inequality. So that was the title of the paper. And in order to prove that, we had to prove something like this. So out of a covering, a weighted covering, you can produce a genuine covering with some bound over summation of diameters to power s. And you would definitely know by this point, if you're following this channel, that summation of powers of diameters of coverings is an approximation of the Hausdorff measure, which the coarea inequality is basically all about. The proof of this theorem, which was originally given to us by Fedor Nazarov, is one piece of math that I have found extremely elegant. And there are some tricks, so many tricks involved in it that is still elementary, not like big machinery mathematics. It's elementary mathematics, but with lots of twists and creative ideas. That is why I'm compelled to present it here as well. So the theorem follows quite routinely from the finite version. So everything as before, except that the collection of balls you start with this time is finite. In this case, the claim is still similar. So you find the subcollection that covers after 3 dilations. The price you pay for those is bounded by this weighted average. And this time you have this sharp upper bound of 1 and not 8. In the paper we had 2, which was then sharpened by Ivan Violo. It's been never published, that version. And this time around, the balls you pick are going to be disjoint as well. So you are welcome to pause and think about this lemma. What is it surprising? Is it very natural to expect? What would be the difficulties and what not? And then proceed with the proof. Okay, for the proof, we are, of course, going to show that the Bij's for the chosen balls is no more than AI Bi. Notice that Bij's appear here as well, because this is all of the i's. So if you have B3 here, you also have A3, B3 here. The reason you don't get anything interesting from this is that A3 could be a very small number. getting 1/millionth of B3 is no help in covering B3. So B3 has to be covered by the other AIPIs, and you will see that soon down below. So what you do, you say, okay, you need to prove something about all choices of AI and BI. Interestingly, AI and BIs are not connected in any way. None restrains the other. So then you say, let's do it for the worst possible case. The left-hand side has nothing in terms of AIs. So let's keep BIs as they are and look at the worst case, the worst possible choice of AIs that could be out there. If you prove this worst scenario, then definitely you have the others. So you look at this minimum, the smallest right-hand side that you get. Of course, you keep choices bound by this restriction. It's just not any choice of AIs. The first claim is that a minimizer exists. This is because if some AIs are bigger than 1 and you get a covering, then you will get the covering again if you replace them by 1. Suppose, for example, A5 is bigger than 1. So A5 is bigger than 1. In covering this set, if B5 has no contribution, B5, say, does not intersect the set A, then you don't need any help from here. I mean, this does not contribute anyway, no matter how big A5 is, because you get 0. So it wouldn't matter if you replace A5 by 1. On the other hand, if B5 does contain the point X, then this becomes equal to 1 already. So this quantity becomes A5 and it's bigger than 1, so you definitely get that. But you get too much, you don't need that much. If it was 1, if you replace this by 1, then that becomes 1 times 1 is still 1, and you get bigger than 1 that you wanted. So either this is insignificant, or it's too much, and replacing it by 1 still gives you a covering. And if you reduce A values from bigger than 1 to 1, you're also reducing that. So a minimizer definitely will happen within the range of all AI between 0 and 1. And that means you should look for the minimizer in a compact set. This restraint is a continuous restraint, so it's not all of this cube, but a part of it, but it's still a compact part of it. So from that compactness argument, you get that a minimizer exists. And as I said, if you prove something is less than the minimum possible, you have it from a generic value as well. Now suppose that you have fixed one such collection of AIs, which gives a minimum value for this. What is so special about the minimizer? The answer is this key claim, that when you have this minimizer choice for AIs, a very delicate balance occurs between the prices and the weights. Every price, every K, is paid for by the neighboring weighted sum of AIBI. So only the AIBIs which have something to do with BK, that they are neighbors of BI, the ball BK intersects them, are enough to cover BK. So AKBK again is here, but AK could be very small, but the lemma says that in that case, the neighbors, the others will contribute, and again, you will beat the BK by this summation. And that is a big step toward proving that this Bij is less than summation AIBI, because every single one is paid by the neighbors here. And you move to the next BI, it's paid by the neighbors of the other one. One thing that you want to make sure is that you don't need twice anything. You don't need overlap. Maybe something is needed to cover BI1, And then what if you need the same thing to cover BI2? And that will be avoided by the rest of the proof. So under this delicate balance of choice of AIs, you take a very large ball. I mean, not a very large, one of the largest in terms of diameter. So you pick BI1 so that its diameter is largest among all. Then this will be your BI1. And there are some balls which will intersect it. So these are the neighbors of BK. So they can touch it in many different ways, but the radii is smaller. So the worst will be if you have a ball of quite same, well, this isn't quite same diameter. So quite same diameter, and they touch only along the boundary. So this is again touching BI1. We will include this among our ultimate choice of the balls. This is a ball we will pick no matter how pricey it is. BI1, the price for this ball could be the largest among all the balls, but we don't care, we want to buy it. This is because actually it has large diameter, it helps with covering our set A. Let me draw also maybe our set with a different color. So suppose something like this is our set A. So once we purchase this ball, we have to pay for it. And that's where we will bring in this key claim. We will know that the summation AIBI over those i's where you intersect BI1, I1. So when we, at the very end, when we will have all of our choice of balls, we need to prove this, all I. If this is showing that the BI1 part of this, there's the BI1 part inside here, is covered by AIBI, those that are neighbors of BI1. Therefore, if we drop this from here and drop this from there, we are safe. Or in other words, to prove this, because we have this, it suffices to drop this in these quantities from respective sides and prove it for the rest of it. So that's one indication that toward the punchline that we're gonna get rid of BI1 and all of its neighbors. Getting rid of BI1 drops the requirement here, and dropping all of its neighbors gets rid of this part so that we are left with dealing with the rest of the story. So that's only for the weights, so that if I buy BI1, I can pay for it by the neighbors. How about in terms of covering? Because getting rid of BI1, that means I will have difficulty covering the set A, but that's not something that does not worry me because of the following trick. Because BI1 has one of the largest diameters, the worst possible point, the furthest point away among those neighbors is this one. And because this diameter is equal, at most equal to diameter of BI1, that means if I dilate this BI1 by 3 times, I get a ball, which I'm not going to draw on this part, will consume all of BI1 and all of the neighbors. So BI1 union all the BIs which intersect BI1 will be consumed by 3 times BI1. So this red ball, let me again highlight the interior of that, contains everything that has to do with BI1. It contains all of BI1 and all of the neighbors, any other ball that touches it. Now let's look at the set. So let me show you my other lines. This was the part that I just wrote up there. So the remaining balls, it's difficult to read, but I'm reading it for you. The remaining balls with their respective weights form a weighted covering of A minus 3 BI. So the part of A, which is not in the red, so we're talking about, say here, let me switch my color. So suppose there's an X here, which belongs to this A, but not in the 3BI1. So what we had was that originally, if we did a summation over all I, this was bigger than or equal to 1 because it's in A. Now, what if we have the new collection? So has this changed? Okay, let's put it this way. Will this inequality still hold if we drop from the collection of balls BI1 and the neighbors? The answer is yes. For this particular point you see here, BI1 and any of its neighbors, and none of its neighbors, did not contribute to this in the first place. Evaluate X, because BI1, X BI1 is characteristic function of BI1 and characteristic function of all of the neighbors will vanish at this particular X. So this inequality is holds, this summation is bigger than 1, but it's still bigger than 1 without any help from BI1 and its neighbors. Therefore, and this is a typical point in here, not a special one, so every point in A minus 3BI is weighted cover without help from BI1 and the neighbors. So let me, for that, so from the covering, we can drop BI1 and the neighbors, and from the inequality that we will ultimately need to prove, and from that inequality also we can drop BI1 on the left-hand side and the neighbors on the right-hand side. So everything, both in terms of covering and in terms of the final goal, can be dropped from the whole analysis. I am sorry if this was too much of explanation. If you get the picture, it's just so immediate. So let's, without further ado, go to the punchline. We are back in the original situation. We have a set, but this time it's A minus 3BI1. We have a collection of balls, so these will be BIs, except for BI1 and neighbors. So we have a collection of balls, this. We have the weights. Weights are again the same. And we have prices associated with them. And then we have this weighted covering. E is bigger than characteristic function of A minus 3. And we need to prove this, that there is a choice of subcollection such that blah, blah, blah. They are disjoint. 3 times dilation covers this set. And also this summation of prices is less than the weighted sum of the prices. But have we gotten to the end? Well, yes, because all you need to do is to say, okay, I go all the way back to the beginning of the proof and begin by an induction on the number of the balls in the collection. So if you assume, maybe some people call this advanced induction or generalized induction, you assume that the claim is true for n equal 1, n equal 2 until n equal n minus 1. And then you want to prove for the capital N, and the way we prove it is just this proof, because we reduced everything to a smaller number of balls. It's definitely smaller because at least you removed BI1 itself. So it reduces definitely. So you, by induction, you get it for all cases. So that is the lemma, and that one was its proof. This lemma is basically purely combinatorial. It really has nothing to do with geometry, with balls or anything. And hopefully it will find some more applications in future. But until then, thank you for watching this video to the end. Please, I really appreciate any comments, especially on this type of material that hasn't been around in textbooks. If you notice corrections, please point them out to help other fellow listeners. And if you have any other comments, also please do so. But one last request is please subscribe if you haven't done so yet, because that just keeps us motivated to do more stuff like this. Thank you so much.